The story of Planet Vulcan stands as a poignant eulogy in our quest for truth, and while the story carries a hint of melancholy in the ultimate demise of this hypothetical planet, it serves as a triumphant tribute to the scientific method. It underscores that our pursuit of knowledge may not always proceed smoothly, but as long as we steadfastly adhere to the scientific method, it remains an unwavering guiding light, illuminating the path to truth. Join me, the Cosmic Skipper, as we look at how the scientific method led us to hypothesize the existence of another planet in our solar system that we called Vulcan, and discover how, 70 years later, a total eclipse revealed profound truths about the universe, and how these discoveries led to the unravelling of the myth surrounding Planet Vulcan. Our story begins in the mid-19th century, where Newton's laws of gravity stood as the dominant force governing planetary mechanics. This framework received a significant boost from Urbain Le Verrier, whose meticulous calculations not only predicted the existence of the planet Neptune, but also pinpointed its precise location. His calculations were so accurate that within a day of receiving them, astronomers found Neptune exactly where Le Verrier had predicted it to be. Buoyed by the success of this achievement, Le Verrier turned his mental prowess to another planetary oddity, Mercury. For decades, scientists had been puzzled by observations of this planet, as it exhibited an anomaly marked by a slight precession or wobble in its orbital path. This deviation, a subtle shift from its anticipated orbit, could not be entirely accounted for within the framework of Sir Isaac Newton's well-established laws of gravity. Guided by the scientific method, Le Verrier embarked on a journey to decipher the cause of Mercury's orbital behaviour. Through his mathematical calculations, he formulated a hypothesis that an as-yet unseen planet was orbiting between the Sun and Mercury, giving birth to the myth of Planet Vulcan. Given Le Verrier's proven credibility in pinpointing Neptune, astronomers worldwide eagerly embraced the challenge of locating Vulcan. However, time passed and years turned into decades, with Vulcan remaining an elusive and unconfirmed planet. Despite its tantalising theoretical appeal, Vulcan lacked empirical evidence and the coveted confirmation through direct observation required by the scientific method. Nevertheless, with no alternative hypothesis emerging to fully explain these orbital peculiarities, the idea of Vulcan lingered in the background through the decades. But then in 1915, Albert Einstein introduced his general theory of relativity, causing a paradigm shift in our understanding of gravity. In pursuit of unravelling the enigma surrounding Mercury's anomalous orbit, Albert Einstein, much like his predecessor Le Verrier, found himself confronted with a perplexing puzzle. What was causing it? The further he delved into a meticulous examination of Mercury's orbital path, Einstein gradually reached a transformative realisation. The solution to the problem lay not in the presence of the planet Vulcan to resolve Mercury's orbital peculiarities, but in reimagining the very nature of gravity itself. He proposed that the peculiarities observed were a consequence of the bending of space-time, which was caused by the Sun's massive gravitational field. It marked a paradigm shift in our thinking of gravity as it departed significantly from Newtonian gravity, which conceived it as a force acting between two masses. It was so conceptually different that the bending of space-time would not only affect the objects in the universe, it would also bend light around these objects. However, the scientific method dictates that any hypothesis needs to be tested to determine whether it is true or false. And the crucial first test for Einstein's theory of general relativity came with Sir Arthur Eddington's expedition to the solar eclipse of 1919. Eddington, an astrophysicist, reasoned that with the moon blocking the sun's light, he could observe distant stars situated nearby. By comparing their positions during the eclipse to their positions when the sun was not in that part of the sky, he could determine if the sun's gravitational field indeed did bend the light from these stars. A shift in position would provide experimental evidence supporting Einstein's hypothesis. The results of Edingtons Experiment were highly significant, with observations revealing that light from distant stars had bent as it passed near the Sun, aligning precisely with Einstein's calculations. The general theory of relativity had been validated and explained how gravity worked better than the established Newtonian laws of gravity. Einstein's general relativity emerged triumphant, offering a more accurate description of gravity and celestial mechanics. The bending of light, the warping of spacetime, and the redefined understanding of gravitational forces became the new foundations of modern physics. As science embraced this new paradigm, the once hypothesized mythical planet Vulcan faded into obscurity. The need for an unseen planet in our solar system was replaced by the elegant concepts put forth by Einstein's theory. The 70-year journey from Leverrier's hypothesis of the planet Vulcan to Einstein's general theory of relativity reflects the scientific method in action, through observation, hypothesis, experimentation, and conclusion. The story concludes with the sad demise of the hypothetical planet Vulcan, but it also serves as a testament to the evolving nature of scientific inquiry and the scientific method. Thank you so much for watching, and if you enjoyed it, please consider giving it a thumbs up and subscribing if you've not already done so. Your support is greatly appreciated.